Power factor, lead or lag, part 2. Let's take a look at how this could relate, perhaps, in a discussion of power. You'll remember this diagram from previously in last week. Remember how we did the calculation of the current value and the voltage, and we sketched our phasors. To this, we could also add a discussion of power. So remember, when we're dealing with power in AC, there are 3 different types. And when we're dealing with a resistor, the one type of power that we have would be watts. So if I wanted to calculate the watts in this particular system, I could use any number of values here. I could use E times I, so the voltage times the current, or I could take the current squared and multiply it by the ohms of the resistance, or I could take the voltage squared and divide it by the ohms of the resistor. As long as the ohms are of the resistor and the current through the resistor and the voltage across the resistor, we're going to get P, power, watts of power from the resistor. So with my calculator, I'm just going to use these 2 values, 120 volts times 10 amps. This would be equivalent to 1200 watts, and it could also be written as 1200 VA. The reason it can be 1200 VA is because there is no other component in the circuit, and therefore a power triangle would be somewhat useless. So this would be considered a 1200 VA load with a power factor of 1. Well, how would that then be used when we look at the inductor? Well, the inductor, from the previous time we looked at this, we had 120 volts, 10 amps, and we said there was a deflection there between the current and the voltage, and due to that, it was out of phase. And the power factor was 0, and we said it was a power factor that was lagging because we're always indicating what happens with the current. The current is lagging or behind the voltage. So what that means, when we go to do the calculation, is Q, or quadrature power, or wattless power, is equal to the voltage times the current through the inductor. It could also be calculated as the current through the inductor multiplied by the ohms of inductive reactance of the inductor. And it could also be calculated as the voltage squared divided by the ohms, inductive reactance of the inductor. So I'm going to do exactly what I did with the resistor. I'm going to take the voltage and the current that is flowing through and measured across and multiply them together, and we get 1200 VAR. Another way to write this would be to say it's 1200 VA. This is a 1200 VA load with a power factor of 0 lag. Inductors are always considered to be a lagging component. And finally, that brings us to the lowly capacitor, always left till last for some reason. Very sad. And in this situation, again, Q is what we would be calculating, which is VARs of capacitive reactance. So that means that Q, we could take either the voltage across the capacitor times the current through the capacitor. And remember, we still have 120 volts across the cap, right? We could also calculate Q with the current through the capacitor multiplied by the ohms of capacitive reactance. Or we could take the voltage across the capacitor and divide it by the ohms of capacitive reactance. Either way, we're going to come out with VARs. And I'm going to do the same thing as in the previous 2 examples. I'm going to take the voltage and current. So E times I, voltage times current, gives me 1200 VARs. Remember, there's always a second way for me to indicate this, and so that means that we would also have the equivalent of 1200 VA. This, in effect, is a 1200 VA load with a power factor of 0 lead. And remember, we got this lead concept from interpreting the two phasor locations on our Cartesian plane of the current and the voltage. The current is leading the voltage. And if you want a refresher on how those phasor diagrams work, feel free to go back to week number 1 or week number 2, can't remember which one it was, where we had some information about how phasors are referenced. Hope that helps to clarify a little bit on the discussion of lead and lag and power factor.